Hello everyone, my name is Shub Patel. My SAP ID is 56, batch B4. I am from third year of electronics from DJ Sanghvi College of Engineering. In this video, I am going to explain how to design the practical integrator circuit using opamp OP07 on simulation tool LTspice, and I will also explain the frequency response of it. For the construction of the integrated circuit, we will need to calculate the values of resistors and capacitor. For that, let's move to the calculation part. We have been given that Fa equals to 1 kilohertz and Fb is 10 times of Fa, which is 10 kilohertz. We will first assume Cf equals to 150 nanofarads. We know the formula of Fa, which is Fa equals to 1 upon 2 pi Rf Cf. From this, we will obtain Rf equals to 1 upon 2 pi FaCF. Then, after substituting the values of Fa and Cf into this formula, we will get Rf equals to 1 kilo ohms. We also know the Fb formula. Fb equals to 1 upon 2 pi R1 Cf. So, R1 equals to 1 upon 2 pi Fb Cf. So, after substituting Fb and Cf, we will get R1 equals to 100 ohm. The offset resistor, which is ROM, is the parallel connection of R1 and RF. The value obtained is 100 ohm. So now we are done with the calculation. So let's move to the LTspice software. I have already constructed the practical integrator circuit. This is the feedback resistor and its value is 1 kilo ohms as calculated. This is input resistor, its value is 100 ohm. This is offset resistor, its value is 100 ohm again, and this is CF, which we assumed as 150 nanofarads. We have taken input voltage supply at inverting input terminal. To get the frequency response, we will right click over here, click on advanced, go to the AC amplitude, type 1 in this box, click on OK. Now right click anywhere on the screen, click on run, go to AC analysis section. In the first box, select decade. In the second box, type 2000. In the third box, which is start frequency, we will type 1 Hertz. And the stop frequency at 100 kilohertz. Click on OK. So, this is our required frequency response of the practical integrator circuit. So you can clearly observe that the gain initially the gain remains constant at 20 dB, and at the break frequency it drops by 3 decibel 3 dB, and at 10 kilohertz it finally becomes 0 dB. So by choosing different values of frequency we get different values of R and C, and from that we will get uh, different different gain. So accordingly our graph changes. For example, in this case I have taken FA break frequency is 1 kilohertz. So at this particular frequency the value of gain drops by 3 dB, and after that it reduces constantly up to 100 kilohertz, and at FB, which is 10 times of FA, that is 10 kilohertz, the gain becomes 0 at that particular frequency, that is 0 dB. So let's move to the integrated circuit again. Now basically the integrated circuit produces the negative integral of the input signal. So to verify that we will apply a sinusoidal signal. So the integral of sine is cosine, and the negative sign, which is minus sign, indicates that it is 180 degree out of phase. So to verify that, we will apply sinusoidal signal. For that, uh, remove this. Then right click on the voltage supply, click on sign, type 0 in the first box, type 1 for the amplitude and 1 kilohertz for the frequency. Now click on run. Then in the transient section for the stop time, type 10 ms. So this is the input. As you can see, this is the input, which is sinusoidal input we have applied, and the output of it is a cosine, which is 180-degree. As you can see on the screen, the green signal is the output signal and the blue signal is the input signal. I have uh, performed for square wave and triangular wave as well. So let's move to it. So for the square wave as the input, we got a triangular wave as output for the practical integrator circuit. When we applied a square wave as the input, this integrator produced a triangular wave at the output terminal. I have also done for the triangular wave as well. So when I applied a triangular wave as the input signal, I got a sinusoidal wave as the output. This blue signal is the output signal, and this green signal is the input signal, which is triangular wave. This is the frequency response. I have already explained it earlier in this video. At 1 kilohertz, the gain drops by 3 dB and it drops constantly till 100 kilohertz, and at 10 kilohertz, which is FB, the gain finally becomes 0. Let's move to the observation table. This is our observation table. So for different values of frequency, we get different values of gain. As you can see, before FA, our gain was almost constant, but at FA, which is the break frequency, which is 1 kilohertz, our gain is dropped by 3 dB. As you can see, initially it was 20 dB, now it has become 17 dB. Now after this value of frequency, the gain drops constantly to the 100 dB till 100 kilohertz frequency, and also at particular frequency of FB, which is 10 times FA. In this case, that is equal to FB equal to 10 kilohertz. The gain finally becomes 0. The gain becomes 0 dB at FB equal to 10 kilohertz. So that's all in this video. Thank you.